Oh, wait, yeah. I have like, yeah. Yeah, that you can pump out the water that way. Yeah, that's usually part of that. Just kind of back around. Yeah. Oh, okay. Yeah, it's usually how I get my water changed. So like, suck out of the top, whatever. So I'll back. Yeah, that's what they were.
How are you? Enough energy to do something? Or ready for relaxation? When is your next Chem Club?
We just have one on Thursday.
So it's not always on Wednesday.
Tuesday.
Tuesdays.
You are masters of your own club and you schedule it. Okay. So what are we doing? What should we do? Where did you stop?
Stop them and momentum operator.
Okay. So how does it? Momentum. Momentum? We didn't get further. Okay, then, but we will not probably focus on the homework, so we will have more time for this stuff. And if anyone needs some comments about homework, I will be happy. But it is really the much easier. It is less challenge. Okay, I will go to Hamiltonian and evolution operator a little later, and we did cover them already a little bit when going through principles of wave packet propagation, but I will return. What is more interesting and maybe reasonable right now, and for understanding and for successful use of the code, will be the commutation of operators. So, do you have access to the codes? Can you open them from last week?
Yeah.
And let me share an idea, share a comment when I think we're not a big expert, but you may make your own plans and arrangements. It's a little bothering to send same code again and again through email. There should be something like cloud or network space for everyone. And you can store it there and access it again and again. Especially if you do little changes, and if you will stick with the same code and update it every week, it would be reasonable. Is there a thing like that here in this environment?
Maybe you just use my personal one, but yeah.
Okay. Yeah, and another thing is to just install MATLAB on your laptop and PC and then be independent of these facilities. Commutation. What is the expected result of commutation between position and momentum? it is a thing that we all are expected to remember, but I do not remember anything, just derived things if I forget. But any ideas? So it is not 0, right? So if you swap the order of position and momentum operators, there will be something not 0. It would be, probably it will be proportional to Planck constant, right? So what I really do not remember, but we need to either recall it or quickly to derive whether it will be positive or negative, just Planck constant or maybe imaginary unit. Right? So we check on this, and we can prove that the implementation operators that we are using what follows do not violate main principles of quantum theory. Because it would be great to have healthy suspicion at any step that we are doing. So if we identify which variable is responsible for momentum and position operator, maybe it is position operator, momentum operator, and position operator. I will double check. We will double check it together looking through the code. So by setting up construction like that, so we can assign it to a new matrix, like call it home or whatever, and then plot this matrix. How should it look like if everything is good? If it is right? What does it mean if the so operators are typically matrices, and if you're getting a number, what does it mean? Like if you do operation between matrices and suddenly you get, someone tries to sell you that it is a number. Something is wrong. There is a missing step. So what are your ideas? This is semantics. It is not science. It is just skipped declaration. So if someone tells you that matrix is equal to a number, do not believe him. So if it is a number, it means that it is a number multiplied by identity matrix, which has ones on the main diagonal and zeros on the all subdiagonals. So if we are going to identify which variables are responsible for these operators, and I know it is the question that everyone hates, or referral to your memories from previous meeting. Now I hate this referral myself because I don't remember what we were doing a week ago, but I will try to dig it out and find. So first we'll find which variables are responsible for operators, then try to construct the commutation, and then analyze the result of this commutation by doing just by plotting matrix, which you can do by several commands like mesh or bar3. So if you will get a matrix very similar to diagonal with some small number, some factor, good. But who knows? Maybe this approach is either wrong, or maybe it has some limits of applicability. So it will be one of the criterion to judge how good or how bad the approach is. Okay? So you can try it independently, based on your memory or based on your how to say, inspection of the code. So first I want to go to the same directory where these codes are stored. So I'm going to this downwards, and I'm running the one with command. And last time we did disable some setup of the potentials, making that it is applicable to free space. But now I think it is back there, so it does something else. Later on, we will take care of this stuff. Right now, it is applied to one of the examples that we were we didn't cover yet. And if we do not have enough patience, we can stop it at the middle. Oh, okay, it is done. So we don't care about the results of the code. We need just operators. So let's browse through and look for no, we do not need this one. This is in momentum space. Okay, so px is a good thing. Let me write it down. So p sub x for momentum by method 1. And alternative way. So there are two alternative ways of defining momentum operator, and px3. So those are in px3 in line 124. So whoever is presenting it may look in MATLAB help for definition of this procedure. And where do we have the fx? Good. X operator. So here I was right. This is right notation. So I'm going to do a numerical experiment by doing this Px times x operator minus x operator times Px, and assign this into, I don't know, something creative. See. So there is no error, at least, which is good sign. And then I can try to wait. So it is not. It doesn't agree to plot this because probably there are both real and imaginary parts. So if I'm looking for real part, it is not quite what we expected. It is small near the main diagonal, and then there are some non-zero values at as far as we depart from main diagonal. Let's check what it is this imaginary. With imaginary, it is even well, imaginary part is not as close to zero on the main diagonal, but it is somewhat far from what we expected. So even if the this definition of momentum operator will later give some healthy results, we should always put it in doubt, because commutation based on this definition is screwed up. It is not what we expect. So what if we try to use alternative definition of momentum operator? The real part is literal 0, and the imaginary part well, it is not 0. You see that there are some features near the main diagonal. So it is about -1 on the main diagonal. There is additional value at the corner, which could be inherited from periodic boundary conditions, or you may again practice healthy suspicion that something is wrong at the main corner. But near the sub-diagonal elements are zeros, and the real part of all elements are 0, and the main diagonal and actually second sub-diagonal do have -1. So this will correspond to this is would correspond to, what did we try? Momentum, position, momentum equals minus I h bar. So if you are looking on what is going on the screen, you may ask, where is h bar? right? Or if no one cares, I can ask you. So here you see that it is about -1, and you may rotate the image and narrow it down and check whether it is really -1 or something different. But where is Planck constant, which is expected to be really small? Like in joules, it is like 10 to the minus 34 or whatever. So, and here we have -1. What is going on? Any ideas where to look for the answer? Remember, well, now I remember something. I was staying here and making some notes on the units. So if you go to the very top of this code, you see that it does practice the system of units where mass of electron is set to 1 and Planck constant is set of 1. So it is so-called atomic units. And if you need to go back into whatever is more comfortable to you, there should be conversion factors. Okay? So the conclusion is that there are 2 methods. Well, there are 3. I'm skipping the first one completely right now. And the third one gives a little better agreement with intuitive expectations about commutation of operators. Third method is better. Another thing, that commutation is not 0, generally. If you just multiply 2 matrices and then swap order and subtract, it will be not a 0 matrix, it will be something else. Okay? What is next? Hamiltonian, right? So we do need to let me remind, or let's recall together what are we doing. Because otherwise, if we were doing some other tasks, it's really hard to focus. And going to technical details without picture has no sense. So, what are we doing? Generally, what this code is doing, what it's needed, benefits we are expecting. Any ideas, or you want to give me the privilege of thank you. It's kind of good. So, in the pen and paper labs and mass materials, we came to a conclusion that even very small oversimplified systems are really hard to describe. Even if we believe that quantum theory is powerful and thousands of measurements and exploitation, doing anything real is not possible. It's possible, but it takes time. Therefore, we are trying to use. This is very simple. Typically, computer codes are compiled with black box tools, where you just run see what happens inside. Here we follow so the goal, of course, goal of the code is to predict future, to propagate wave functions from the past to the future for specific model. The model is defined by Hamiltonian and pair potential. The restriction here, there are multiple approximations and restrictions. One of the most important is that it is only one dimension. So there are no one-dimensional things in our world. There are things three-dimensional, and one can apply some tricks to simplify things into one dimension. Okay. And in order to predict future, we use least efficient, but most general approach, evolution theory. Right? So we multiply wave function of the past by evolution theory, which changes wave function from the past to the future. Okay? And the evolution operator is exponential with or the power of exponential includes Hamiltonian. Understand? Therefore, we need Hamiltonian. Objections? So, there should be. It's hard to remember all details, but knowing the logic of this code, I can anticipate that the variable for Hamiltonian will be called ham. Not for like type of food, but to have difference from other H symbols. And since you already noticed, so please try to either memorize or make notes, especially if you're a presenter of this subject. So as you may have noticed, there are alternative ways of determining, of defining the momentum operators, right? And you already noticed that quantum commutation based on these different operators gives different results. So we are trying to model the same momentum operator, but with different precision. If there are two types of two implementations of momentum, how many implementations of Hamiltonian will be? 3. Why 3?
Because I'm looking, we have M2 and M3 on variables.
Yes. So I'm skipping the ham. This later on, if you're interested, you can either study yourself or I can privately tell. But if you go to simple ham without 2 and 3, it will be too complicated, too long. It will be like extra credit stuff. So, if there are 2 ways of implementing momentum, there will be 2 Hamiltonians. Okay, for those who are reading the codes and are interested, the first method is based on evolution in momentum space and then converting the results into coordinate space by Fourier transform. But the first method is absolutely perfect if we want to model free space, particle in a free space without potential, but it is very uncomfortable if you want to do anything else. So first method is only benchmarking tool, which is applicable only to free space, while second and third are general. They can be right or wrong, but you can apply them with any shape of one-dimensional potential. So, since there are 2 momenta, there should be 2 Hamiltonians, right? Ham2 and Ham3. And in both cases, we will use kinetic plus potential. The difference is only if that squared, and then we need to take care of the constants. So minus h bar squared divided by 2 mass. We know that h bar and mass will be 1, so it will be something simple. Plus, so before going to the step, we already need to have potential defined. These things are simple. They're just interconnected, and if you start from the very beginning, it will be very boring. And if you start from interesting things, then many introductory things will be missed. So it's thing. What is potential? Potential energy. Well, mathematically, which type of data it is? If there is a one-dimensional coordinate, huh? It is spring, but numerical. If our coordinate is just a set of different values of coordinate, it is digitized, discretized, right? x1, x2, x3, right? Then the potential, if our coordinate is represented by x1, x2, x3, x4, xn. And by the way, I remember writing it last time. Like we can have it 0, delta x, 2 delta x, 3 delta x, right? Remember. And then if you do have a potential, we want to be arbitrary, to have arbitrary ability to describe arbitrary potential, not only quadratic for harmonic oscillator or 0 for free space. We want to describe anything. Therefore, it will be just values, like V1, V2, V3, V4, V. So it will be just array of the values of potential at a certain point, right? One-dimensional array. If you have position is one-dimensional array, then potential will be also one-dimensional array, right? Okay, it is what I wanted to hear. Now, based on quantum theory, we need operators which are matrices. So, is it a paradox? Potential is a vector, it's just a function, and we need a matrix. What do we do? So the following question is more like a programming question, it's not big math. Yeah, exactly. So let's assume that it will be matrix with zeros off the diagonal and these values on the diagonal. Okay? And there is a command in MATLAB to do it. So just do diag of V. And variable V should be defined somewhere before. How to define this variable? You can just write a function like V equals x squared or x minus x naught bracket squared or something more complicated. For those who present methods, it is a very secondary question. In your research projects, this definition of potential will be the only aspect of creativity. The rest you just follow the procedure. So you deal with it again and again. So we should identify a line that looks like this in the code. At least it is what I'm going to do. Huh? Oh, thank you. Well, let me check. Is it really 110? Yes, it is 110. Alex plus 1 for reading the code. Oh, I lied. You need this h bar square and minus only if you are putting the derivative. But if it is just momentum, it is just px squared divided by 2 times mass. You lost the chance to catch my error in this aspect. But I will do more things for you. So Hamiltonian. Now, what is evolution operator? And you know, when you do presentations, everyone from previous years wants to show codes, especially long parts of codes with tiny font without any comments, thinking that it will impress the audience. It will be not visible. If you really want to show something, show a couple of lines, make it huge font that it is really visible. And it is much better to just show a question. Withdraw, erase last word. Equation. So what is the equation for the evolution operator? Where to look for it? No, evolution.
79.
No, I know which line. What is the equation for evolution? It was given first a couple of seconds.
Is that the wave function of t plus delta t equals e to the negative pi over h bar times Hamiltonian times delta time multiplied by the original wave?
It sounds right, but if you want me to be a robot to whom you can dictate, then please dictate slower.
Okay. Just making sure. So it's exponential, and the exponential is negative I over h bar. And then Hamiltonian times delta t. And then that, all that exponential is multiplied by the original wave. So it's times 0.
Yeah, correct. So it is evolution operator that propagates from time t to time t plus delta t. If you really want to impress your audience, if there will be like some professional theorists who may join your presentations, you can, instead of this simplified, you can write minus I over h bar integral from initial time to final time Hamiltonian as depending on time times d eta. But in case our Hamiltonian is time independent, and in case our increment of time is really short, we replace it by something simpler, right? So the challenge is that H is matrix, right? So instead of H, it is CHEM2. So who was presenting the function EXPM, matrix exponential. I know who, and this person is not in at the meeting right now. It was Ben. I do remember he was presenting it. So if you know there are functions like sine, cosine, polynomial that can be, but if the argument of a function is a matrix, one may need special way to define the function. So exponential of a matrix is a way of using the unitary matrix plus matrix in the first power, I put A, plus 1/2 matrix divided by itself, plus so forth. So use Taylor expansion of exponential, and instead of x, plug in the matrix. So the result of this function will be matrix. Right? So if the Hamiltonian is a matrix, then exponential of Hamiltonian should be also a matrix, because it will act on a wave function which is a vector. Okay? So what is in the code?
79.
It could be in the 79, but let me invite you to the line 112, right below the definition of the Hamiltonian. So here is your second Ham, and here you just plug in this second Ham into matrix exponential, EXPM. So it is exactly what Alex dictated to me when I was playing a role of writing a robot. So exponential minus imaginary unit times Hamiltonian times tau as a increment of time divided by h bar, right? So if we do have curiosity, we may try to plot both Hamiltonian and evolution operator. But I'm not sure if it will look spectacular. So, and if you are presenting this subject, you may want to screenshot of these things and then plug them into PowerPoint, so that if later you will not have time, you already have something prepared. So figure and mesh second hand. Okay, it was expected that MATLAB doesn't feel comfortable of plotting Hamiltonian, because generally variables do have real and imaginary parts, and our human vision is not supposed to focus on imaginary things. So real part has some specifics, something very close to main diagonal, and then it departs to 0 on the off diagonal. Let's look at the imaginary part. Okay, it's also bigger near the main diagonal, but it is substantially smaller. Let's look on the so it is kinetic operator plus diagonal of V. So we can, if you would apply this code to the free space, V will be 0. If it will be harmonic oscillator, it will be quadratic. here V is some couple of steps functions that we were showing on the board. And now if we do the same thing as we did for Hamiltonian, diag of shouldn't be plot of it should be mesh. So you see, it is the same line that was along the main diagonal. It repeats the pattern of potential. So one constant, step up, another constant, step down, then another constant. And everything away are zeros. So it's contribution to the operator of potential energy. Yes? It was a question or just yelling? Boring. Oh, we may check if how does it look for G tau 2. Okay, it's not super impressive because it has so many fringes that, and it is not intended for human eye to interpret. So the major contribution is near the diagonal, and as far as we go further and further away from diagonal, it gets less and less, which means while acting on the wave function, it will perturb the local perturbation. It will intermix values at nearby positions. Anything else for this? So we covered commutation, Hamiltonian, and evolution. The last thing is conversion of operators between momentum and position. Maybe, I don't know. It looks like too many things on one person. We need to, you may want to redecide, or proportionally give substantially more credit to the person who's presenting this. But it will be fair to do a little redistribution. We'll come back to it, but I'll continue presenting right now. So, conversion of operators between momentum and position, it is a subject that Alex raised. It is related to CHEM without number. So this is not very practical, but it could be educationally important thing. What is Fourier transform? Did we cover it in class and in homeworks? So what is it? I do not want to affect your personal freedom, but I just want to share my experience of being undergraduate. During my first semester of first year, I didn't fail completely, but it was not perfect. And then I was collecting things how to survive, and one of the solutions was to every day after the lecture come and read everything that was written in the notes, and maybe even rewrite it once again into another notebook or on the opposite page. So it's a personal freedom, but sometimes if you look back with assigned time, it helps to survive later. Well, I'm done with this comment. So, what is a Fourier transform?
Decomposes a function of time into frequencies and leave it up.
Based on your direction of your glance, probably it was Wikipedia.
Yes.
By the way, some people think that Wikipedia is evil, not for quantum theory, not for math and physics. Math and physics and chemistry articles in Wikipedia are really good. Sometimes they're much better than any textbook. So you can rely on them. And, one can put a mosaic, little tiles, a little bit from one source and another from another source. And, but I don't remember finding errors in Wikipedia on this quantum theory. Sometimes it gets too many boring details, but either I was not careful enough or there are no errors. So it's good. So Fourier transform is converting from time domain to frequency domain, or backwards, from frequency domain to time domain. Did you practice FTIR? Maybe some of you. So what is it? FT is definitely a Fourier transform. What is IR?
Infrared.
Yes, infrared. So one looks how things are vibrating and then converting it into frequency domain. But mathematically, it doesn't necessarily, Fourier transform doesn't necessarily a conversion from time to frequency. It can also be from position to momentum space. It was, I think it was homework number 2, when we did Gaussian wave packet in a free space. And we practiced expansion coefficients, right? Initial condition, expansion coefficients. That, how were we finding them? Let's browse through space of your memories. If you're not reading the notes, maybe it's much harder. Or there is nowhere to browse. So, a little review of what was more than a month ago. There was initial condition phi naught of x equals e minus x squared. And then we needed to practice phi of t comma x equals summation expansion coefficient times e minus I over h bar energy of the state k times t times eigenfunction number k. Remember? Okay, and there the wave function was just plain wave, ikx. The e sub k was something like k squared times some constants. And the question was how to find c sub k. Right? So this expression could be made as integral over dk, and c can be c of k. So result of this integral, so there is a function in momentum space, because it doesn't depend on position, it depends only on k. and k is by factor h bar is the same as momentum. So it is in momentum space. And this exponential of ikx is standard factor in Fourier transform. Right? So the equation that you practiced in homework and successfully completed based on gradings that you gave to each other. This is Fourier transform of this function in momentum space into the function in x, into position space. So from momentum to position space. And when we needed to find this C of k, which was something like k e to the power k square multiplied by sigma. We were practicing inverse Fourier transform. The integral of this phi x naught e to the power, one just flips the sign in front of this imaginary thing, and integrates over x. So if we integrate over x, we convert from position to momentum. And if we integrate over k, we convert from momentum to position. Right? So it's, this is just Fourier transform. Questions, objections, protests, declarations that it is too much. So, prepare to be surprised. I've seen that we may have different representations. Representation in the express wave function in coordinate space or in momentum space. But wave function in our simplified one-dimensional theory is a vector. What if we need to convert not only wave function, but all theory, including operators, from coordinate space to momentum space? How will we formulate Fourier transform for converting operators?
Repeat the question.
Huh?
Can you repeat the question?
I was preparing home to formulate it. No, I already forgot what I told. Okay. We do have procedure to convert wave function from coordinate space to momentum space. And we do have procedure to go back. Now, if you want to convert operator from coordinate space to momentum space, how would such transformation look like? Did you get the question? Huh?
That's what I gotta think about that.
Yeah. Did I surprise you? And I don't know where to write. Whew. So, if we have one dimension, our wave function is one dimension, and for each dimension, we in order to practice Fourier transform, we need to take our source function, multiply by exponential and integrate, right? One integral and one exponential per dimension. But matrices, in some sense, they are two-dimensional, right? Because there are rows and columns. Convincing? So how many times do you need to integrate the matrix in order to convert them between position and momentum? Yes, you've got it. So this year class is prepared better than previous years, objectively. The only problem is with remembering what was before. Okay, so suppose that I do have, will you see if I write something here? And yeah, I can also focus the so suppose we do have some useful operator already cast in momentum space, right? So it will be a matrix in momentum space. So we need to have indices, rows and columns, but they will be like K1 and K2, or K and K prime. Let's call it maybe, I don't know how to call it, letter A. Operator A that depends on K and K prime. So it is operator in momentum space. Operator in momentum space. Now, we do want to convert it into operator in the coordinate space. So we want to convert it into A of x, x prime. Same style as we had this CHEM evolution P operator. So if our hypothesis, everything was correct, we need to multiply it. So here I multiply it by e to the power I k prime times x prime, and I integrate it over d k prime. So by integrating over k and having it multiplied by this exponential, I convert it into the function of x, right? So this exponential has both momentum and position, and it helps to convert. And here I will write integral from over k1. Now, I will write on different sides, otherwise it will be too messy. On the other side, I need to convert variable k. I need to multiply integral over I k without prime and x without prime, right? For this independent variable. And I can put at the end of the message dk. And here another integral over k. So we have two integrals. If you want to see, we have two integrals over k and over k prime. And we have two exponentials, one with k prime x prime and another with kx. So if you perform this operation, it will be two-dimensional Fourier transform, and it will convert operator from momentum space to operator in position space. Make sense? Let's check if this idea was already implemented in the code. here it is. So we spent so long time to discuss it, but it is just this expression. So the multiplication of matrices or matrix by vector is equivalent to integration if we are in discrete space. The POP is momentum operator in the momentum space. If you roll back, we will see that momentum operator in momentum space is really simple. It will be same as position operator in coordinate space. It will be just diagonal ramping up, and everything else is zero. And this W and W prime will be just exponential that depends on both position and momentum. Okay? So if things on this board are correct, we may scroll up and find W, capital W, double Y, W equals to exponential of IKX. Let's check it. And now you are jumping to much higher level than any students in any of previous years. I was skipping it before, fearing about the psychological health of students. But I see that this year is much stronger. So, if we do have this factor e to the minus I pi divided by number of points, and you will multiply by different, multiplied by itself several times, or put into the power that would include different number of steps along position and along momentum, this matrix will become equivalent. So this R is elementary step along position and momentum, and this is a combined power. So we step some negative and some positive along both position and momentum. So this W will be two-dimensional matrix of IKX. And if one wants, one can plot this and check if it is really corresponds. Whew. I don't know how about you, I'm tired, I'm ready to go forward. So, notes, good memories. I'm going to finish this section and go to the next one. Well, modeling quantum dynamics of an electron, it is the same as principles of wave packet propagation. So Bill is saving Alex from presenting it. You may talk to each other how to reorder things, or we can sit later so to make presentations more or less even. Because right now, I know it was a free will choice, but it is objectively the hardest part. So, modeling quantum dynamics of electron, you already know it. You just multiply with function by evolution operator and repeat it again, again, and again. That's done. Now, initial conditions. How to select initial wave function? So if you have volunteers for the subject, you may have an idea. So which we are not yet rich in a sense of literal examples of good wave functions. We had like half period of sine as a ground state of particle in the box, and we had Gaussian function for harmonic oscillator. And we have plane wave, right? We haven't experienced anything else. So, what would be reasonable to? Oh, it is already written here. I was asking a silly question because the answer is already written. So it is really reasonable to assume that dynamics starts with Gaussian for certain purpose and reason. If we know that electron is more or less localized in a certain space, region, and we know that there is a uncertainty principle by whom? Heisenberg. Yes. If there is a Heisenberg uncertainty principle, it means that there will be uncertainty in the initial position. Therefore, we cannot assume that electron is 100% at one point of space. There will be little distribution of being nearby. Right? So we need to set up wave function at time 0 as Gaussian wave function. That's it or not?
Is that all you would want for that point?
You shouldn't care about me. You should care about ability to predict future for realistic systems. You already know what would happen to Gaussian wave function if it is left alone. But we may want special Gaussian function, a Gaussian function that will correspond to electron that moves somewhere. It's non-zero momentum. So it should be Gaussian function localized in space, and it should be Gaussian function that corresponds to motion in a certain direction with non-zero momentum, non-zero velocity. So how to insert momentum into equation for Gaussian wave function? I'll just make a screenshots and maybe share it with everyone, just in case. Because it will be not covered in class lectures. So which question I was thinking about? Initial wave function. There are no problems to set it up if it is a static Gaussian wave function, right? You just exponential minus position squared over some width. But how to model a Gaussian wave function that will move somewhere? Did you try to launch the code? Did you? have you seen stuff moving across? So there is a non-zero momentum. How to set it up into this equation? So if you just multiply Gaussian wave function by plane wave where P is not operator but expectation value of momentum, it will immediately make, you know, the fringes in the wave function means it moves somewhere. So you just need to multiply Gaussian by plane wave. What else? What else is important for initial condition? Sometimes we may want to set it up not at the origin, but somewhere shifted, right? For example, if we want to model harmonic oscillators that was originally elongated from equilibrium, right? So instead of x squared, we can put here x minus x naught, or original expectation value of position, and then square. And of course, there should be some normalization factor, since why we need normalization?
So we only find get rid of the wave function and goes away.
Huh?
So it becomes normal, so we can actually get rid of the wave function.
And find,
Expectation.
yes. So normalization is needed because later on we may want to find expectation values. So this equation already addresses the question here. Initial wave function is chosen as Gaussian, right? It's still Gaussian. The maximal power in the exponential is second, x squared, right? And this IXP can be submerged into this bracket to identify full square, and it still will be Gaussian, just shifted both along real and imaginary axis. But mathematically, it's still Gaussian. So let's find where it is declared in the code. Whew. Font is too large. I will downgrade to smaller one. Can you see the size of the font? So let me invite you to the line number 66. So what do we see here? How to interpret? So, do you see any similarity between this highlighted expression and this boxed formula?
I see the I see the Gaussian wave function.
So you see this exponential of minus x naught squared, right? So this will give you Gaussian profile. Do you see the plane wave? Just before it. So exponential of p naught, which is expected to be momentum at 0 initial time, multiplied by x minus x naught, with its initial position of the packet. Good? Make sense? And the rest stands for normalization. So let's count open, open, close, open, close, close. Once again, or exponential ends and 1, 2, here. So this stuff, this power 1/4, by the way, it looks, you have already seen power 1/4 today in the lecture, right? When we dealt with normalization. So this factor comes of normalization. This x var is the width of the wave packet, which you also can vary if you want to specify level of uncertainty. Smaller width, more certain. Larger width, more uncertain. Right? And this square root of dx is why do we need it? Yes. Why square root of dx? Because when we are normalizing, we are taking wave function squared. Square root of square root will be dx, and then we perform summation of so many infinities or more. So it's just the same dx that is practiced in the integration, right? So if you want to present the stuff, you may plot the psi naught function and make correlation how it looks depending on the parameters. So let's do it. So if you're going to do it right now, you may decide to make screenshots and save them for the future. So what's the name of the variable? Psi naught. Psi naught. Will it plot it or will it say bad words to me? Huh? It plots, maybe. But often it complains, okay. Does it look like Gaussian wave function? Why? We already practiced this stuff in one of the labs. Because wave function has real and imaginary part, and right now it skips z dependence. It makes it projects it in the real and imaginary. If you would look onto plot 3, no. Okay, plot 3 of real. And imaginary and x. Okay. It still doesn't look like Gaussian, but you see that there is a x independent variable, and then there is a real and imaginary part, right? So if instead we will plot only real, if you have one function, if you will plot see that real and imaginary parts are phase shifted. But now we may be interested on the amplitude, like both real and imaginary. What if you do x, comma, absolute value of C naught? So this is real squared plus imaginary squared. And you see it repeats Gaussian shape. So it's absolute value counted from origin up to summation of like length of a vector with the sides of real and imaginary part. So all these oscillations will be inside, below this envelope function. So what would change if we identify a piece of part of the code that is responsible for the value of P naught and redraw this function? So P naught is 0.4 something. What if we do it like 3 times bigger? What is going to happen? How the in the line number 5 there is an initial momentum. Right now we did plot the initial wave function before any dynamics has started. How the this initial wave function will change if you increase momentum 3 times?
Will be shifted over.
No. It is if you change initial position, then it will be shifted. If you change width parameter, it will become broader. But if you change momentum, how the shape of wave function is related to momentum? Look at here. So bigger momentum would mean quicker oscillations, more denser fringes. So if I will run the code again, or I will just maybe run it for so I do not need to watch it until the bitter end. Actually, I can push Control C. Probably runs not long enough. Then now I'm returning to the original image, and now I'm typing hold on to keep the old image and practicing the same command again. You see a big mess. But if I remove old one, I will just make new figure. you see the Gaussian wave function has the same envelope, but real and imaginary parts oscillate quicker. A larger number of fringes per unit length is responsible for higher velocity, for higher momentum. And if we later apply quantum propagation with evolution operator to this function, you have seen that it was moving across the simulation cell like crazy several times. So increasing momentum means developing denser fringes. Make sense? Did you practice this thing? Let me walk around and see how you practice it. And it will be a little excuse for me to take a breath and relax for a minute. And then we'll go further along the list. Yeah, maybe one needs separate just in the way change this. can something's a bit tired, exhausted under the
Very
pressure
tired.
of many.
Not a lot of pressure,
Yeah.
it's very tired today.
How many classes do you have?
Today's my busiest day, so I have class from 10 until the end of our class, and then an hour break for lunch, and then I have class from 1 until the end of this class.
So 4 meetings.
One lab. So it's not too bad. I like labs. Still a lot of class.
Were you able to put this stuff? Were you? Did you notice it? Open. Yeah, and how are you building the space? Well, it's specifically saying you just now.
Yeah, I was watching, I just, I understand.
There's different time slots.
Yeah.
No, if I see this figure with you
Yeah, we wouldn't.
on the same page.
Okay.
Either 4:35, 6:30, 6:35.
Remind me tomorrow.
Always look out.
You always have it at that time.
It's never.
No, it's bad Discrete.
I'm missing see you in this, Alex.
What is next?
Alternative methods to.
What are they? How do you think? It's second hem and third hem, right? It is what we already covered. So depending on how you define the momentum, inherits into kinetic energy, Hamiltonian, and evolution. And therefore, when you, if you have seen, when you run the code, there are two wave packets instead of one, and they're moving simultaneously. Initially, they coincide, and then they start to diverge. And it looks like they get some fluctuations, some errors, and each of them get their own errors, which do not coincide, right? So you can just include a movie of this wave packet and point. Here they are diverging because they are different methods. Nothing is perfect in this world. The only perfect thing is method number 1 with hem without numbers, but it works only for free space when potential is 0. And this hem propagation in momentum space basically is the same as we did in class. It's just finding solution in momentum space where expansion coefficients, distribution in momentum space doesn't change in time, and then converting it into position. So it's only a reference point. So method number 1 is just reference point to debug code on example of free space. But methods 2 and 3 are universal, and they just they're different by the way momentum operator is defined. Okay. Discrete representation of wave functions in space and in time. What is it? I don't know if Ben is watching or watching the recordings, but we need to quickly go through it anyway. Even if Ben is not presenting, we need to be aware of things. So, position is discrete. Same is time. Because in computation we do not have anything continuous. We have only discrete slices. So, upon completion of the simulation, there should be either wave function or probability distribution or both stored as two-dimensional matrix, as a two-dimensional object. Let me point your attention onto this figure. So I'm getting a break for maybe 40 seconds, and I'm going to reproduce this figure once again in at a different aspect ratio, and then we will discuss it. And don't forget about loop. So this loop over n tau is number of time steps, discrete time steps. Each time we come through the loop, we propagate first forward by delta t, and delta t is denoted by the variable tau, which is also defined at the beginning of the code. Ah. Whew. This is sweet. Discrete representation in space and time. So the lines 241, 242 are accumulating probability distribution after completion of each step of each loop into bigger matrix that is called S3. So the number of columns in this matrix is equal to number of grid points along coordinate space. number of rows increases by 1 at each time step. So totally number of rows will correspond to number of time steps. So this is a matrix. Here you see it is 200 by 700, where 200 is number of grid points along position. Later on you can modify these values. It is just selection. So there are 200 coordinate space. And the loop was running for 700 steps. So what is blue and what is yellow?
Yeah, yes, yellow is high probability of that position.
Mm-hmm. And blue is 0, right? So what does it mean, how to interpret the slope?
Oh, is that the rate it's moving?
Yes. So if it would be staying still, the yellow stripe will go vertically. At each point of time, it will be the same distribution. And maybe, as you know about electron in free space, it will increase with, just as a jelly, it becomes a little broader. But we have non-zero momentum, therefore it moves. Moves, and then later on, due to periodic boundary condition, it reappears from other side. And probably after a long time, there is accumulation of errors and we cannot trust it. But originally, it looks reasonable. Okay, so this image is nothing as a big matrix, non-square. It's a little longer in Y, and each point corresponds to probability distribution value at a certain point of time and space, right? I'm done. No, not completely, but with this question. So, any objections or questions or something that hints what is missing? Discrete, position discrete, time discrete. Propagating forward. Make it nice figures. Good. And here's the command. So view 2 is just to have to look on it from the top. If you do not put this command, it will make some side three-dimensional view. So it's three-dimensional, but in some sense it is harder to interpret. Right? So it's Gaussian wave packet moving, but it's too complicated. And if we need to change number of grid points, one is modifying the parameters at the beginning. So number of discretization along X, discretization along time. Time step, 0.1 atomic units, and the step in position also should be defined somewhere. Oh, here. The variable L defines the size of the box, and dx is size of the box divided by number of points. Okay, everything is defined now. Normalization of wave function in discrete representation. It is a task of Ben, but Alex knows the answer. We discussed it, and you gave signs of understanding, like at the right time. Remember, in your definition of initial wave function, there is a square root of dx. Right? So depending on how dense discrete points are spaced, this dx changing. So the distance between discrete points affects normalization factor, both in the initial wave function, and later on it affects any procedures of finding expectation values. So this dx, distance between the points, is hidden already in the definition of the initial wave function. And since we are applying the evolution operator which doesn't change probability, overall probability, the integral over probability distribution on x at each point of time should be equal to 1. One day we may check it. Done with normalization. Size of the simulation cell versus time of simulation. What is it? If we go to this figure, and I will redraw it once again in two-dimensional fashion. We are modeling a molecule or some maybe piece of solid in the center of the cell, but far away from the center. We want to be nothing, to be vacuum or solid. So this reappearance from the opposite side is a little undesired effect. There is a way to avoid this undesired effect and to have our modeling more reliable. First, we can define our box to be bigger, right? Just to increase dx. Second, we can just limit our simulation by such duration that it will be shorter than the time needed to reappear from other side. Right? So if we want to make scientific exploration in a certain range of initial momentum, we take the maximum momentum, look how far it will go from initial position to the edge of the simulation cell, and limit amount of time steps to the values less than this time. So then we will stay in the trustable regime, because after this point of time, things become strange. Wave packet reappears from other side, which is like doubtful. So we did cover. We did cover size of simulation cell versus time of simulation. 5 minutes. Accumulation of expectation values into array of data for the whole trajectory. Dylan? How would you do it?
Honestly,
I wouldn't do it.
yeah, good idea.
No, it is. I congratulate you with selecting a really easy part. So, probably it will be the last thing we do today, and then we'll depart in peace, because our brains will start boiling very soon. So, I'm going to navigate to the part of the code close to the end of the loop. So you see, when you start the loop, this tool for editing draws a line. Where will be for, it means repeating. Where will be end, the line will end. So I'm just going as long as this line goes. Go. Okay, so it is not very long. It lasts for like 100 steps. This trick, opening bracket, making bigger object, making smaller object, closing the bracket. It's a trick to accumulate, to grow your array, to add new value. Here we were growing two-dimensional array by adding new line, but one can practice it much simpler, just growing one-dimensional array by adding new value at each time step. For example, if we need to find expectation value of position. Expectation value of position. Okay, here. I'm inviting you to the line number 208. If you take probability distribution computed by method 3 and multiply it by range of values of coordinate, and then practice the summation, it will be expectation value of where wave packet is, expectation value of position, right? But there is a big problem, not for science, but for our comfort as programmers. This is only one number while we are running through the loop. One number. And we may want to reproduce trajectory at each point of time. So we need to save or store this value each time we are coming through the loop. So if we are practicing, so here is this AVG3, we are putting new array AVGS, which S like plural, many of them. And each time we are coming through the loop, we are adding this value. So AVG3 will be just one number, and AVGS will be array. So if I'm opening new figure and making this plot, AVGS3. This is a big success. Right? You can interpret it, right? So maybe it's better to look on it by rotating it by 90 degrees, but we start at position 30, then it linearly grows, and then it reappears from other side of the box. But here, to some minor little extent, we complete all purposes of the course. An example of completing purposes of the course. You predict the future and you find expectation value of an observable. So if you have an instrument to find position of electron, set it up in the right potential, and measure it again and again at different time steps, it will be what
call
you
will be
get.
disconnected.
Of course, it is oversimplified problem for education problems, but we are using all power of quantum mechanics. We are predicting future. We are finding expectation value, which is a valid thing. And we are doing it again and again at different time steps. And in order to practice it, we needed to accumulate stuff. Hope you have some energy to practice relaxation after a heavy day. See you on Friday.
That's not my